This section we're going to review momentum. If an object is moving, it has momentum associated with it. Momentum is basically the product of its mass times its velocity. So for example, this baseball, a 2 kilogram baseball moving at 4 meters per second, will have a momentum of 2 kilograms times 4 meters per second, or 8 kilogram meters per second. If this moving object collides with something, either a wall or another ball, then during that collision we say there is an impulse of collision, during which time there's a force acting on the ball for some length of time t, and this results in a change of momentum of the ball. This is called the impulse, the product of the force times the time the force acts, resulting in a change of momentum of the ball. So here is an example of a baseball player changing the momentum of a ball by applying a force of, say, 5 newtons by the bat. The bat applies the force on the ball, and if the bat stays in contact with the ball for 4 seconds, which is kind of long in a real-life situation, but there will be a change in momentum of the ball with 20 newton seconds. So let's do a real problem. Supposing a baseball arrives traveling at 40 meters per second, and the baseball player hits the ball, so that after hitting, the ball goes back the other way at 49 meters per second. The mass of the ball is 0.14 kilograms. And let's assume that the ball stays in contact with the bat for 5 times 10 to the minus 4 seconds. And the question is, if that's true, what was the average force acting on the ball during the time the bat was in contact with the ball? And so basically we're going to say that the impulse of the collision, force times the time of contact, is equal to the change in momentum of the ball. So to calculate the change in momentum, we need to know the change in velocity. We know the time of contact is going to be 5 times 10 to the minus 4 seconds. The mass is 0.14 kilograms. And the change in velocity of the ball, let's see what that is. Well, it's the final velocity, which is 49, minus the initial velocity, which is minus 40. Because the ball is traveling to the left, and let's assume left is the negative direction and right is the positive direction. So the change in velocity of the ball is actually 89 meters per second. So just doing the algebra, the impulse of the collision is just the average force times the time the force acts, and that is equal to the change in momentum, m times delta v. And the average force, therefore, will be m times delta v over delta t. And putting in the values for m, 0.14 kilograms, delta v, 49 minus a minus 40, and for the time, 5 times 10 to the minus 4 seconds, we find the average force during contact is 2.5 times 10 to the 4 newtons. Let's do another example of impulse. Supposing we have a 1,000 kilogram car moving at 5 meters per second, hits a wall, comes to a full stop after hitting the wall. What is the impulse of the collision? Well, don't forget what the impulse is. It is just force times time, but it's also equal to the change in momentum. So basically we need to calculate what the change in momentum is. It's a 1,000 kilogram car, and the change in velocity is very simple. It's 5 meters per second. It changes from 5, that's the final. The final is 0, the initial is 5 meters per second, so there's a change of minus 5. So the magnitude, at least, of the change in momentum is 5,000 Newton seconds. Now, supposing things were a little different, right? Let me just circle the answer, that the answer is 5,000 Newton seconds. But now let's assume that instead of the car hitting the wall and stopping, that it actually bounces back. And let's calculate now the change in momentum. Well, the only difference between the problem we just did and this problem is that J, force times time, is equal to m delta v. But now delta v is the final, which is minus 4 meters per second, minus the initial, which is plus 5 meters per second. So the change in momentum, the change in velocity is minus 9 meters per second. So this will be minus 1,000 times 9, or 9,000 Newton seconds. So you can see the fact that the car bounced off is a much larger impulse of collision. Let's see. Let's assume that during this collision, the car is in contact with the wall for 1/10 of a second. Let's try to calculate what is the force during the collision. So stop the tape and see if you can do this, and see if you can get one of the answers. So we're going to calculate force times the time is equal to change in momentum It's a 1,000 kilogram car. The change in velocity is 5. We calculated that. And therefore, if the time of contact is 0.1, then the force is equal to 50,000 newtons. Of course, if you do it for the other example, then Ft equals m delta v. If the time of contact, the change in momentum now is equal to 1,000 times 9, and if the time in contact is 1/10 of a second, then the average force is going to equal to 90,000 newtons. If the force of contact is smaller, for example, instead of being 1/10 of a second, it was 1/100th of a second, the time of contact, then you can see that the force is going to be much bigger. So let's change this to 1/100th of a second. If you now solve for F, you would get not 90,000, but you would get 900,000 newtons. Let's do a couple of conservation of momentum problems. When two things collide, because the forces of collision are internal forces, there is no net outside force. That means the total momentum before collision equals the total momentum after collision. So let's take the case of a 1,000 kilogram Volkswagen heading east at 20 meters per second collides head-on with a 3,000 kilogram truck heading west at 20 meters per second. Let's assume that this is a completely inelastic collision, which means they stick together colliding, and the question is, what is their joint velocity? So we know that the total momentum before collision equals the total momentum after collision. Let's write the momentum of each of the cars. So the Volkswagen is m1, has a velocity v1, and the truck is m2, has a velocity v2. And after collision, they both move off together. So the total momentum is m1 plus m2. They move together as 1 times their joint velocity v. We put in the numbers for m1 and v1, and I'll pull it out over here. (1,000 times 20 plus 3,000 times minus 20, because the truck is heading to the left, equals m1 plus m2, which is 1,000 plus 3,000 times their joint velocity. Solving that equation, we see that their joint velocity is 10 meters per second, and it's minus, meaning it's to the left. So if we look at the answers here, we can see that after they collide, they both move to the left with a joint velocity of minus 10 meters per second. Let's look at this case where after collision, they both head toward each other, but after collision, the truck just stops and the Volkswagen just bounces off. So once again, the point is, what is the velocity of that Volkswagen? So the total momentum before collision equals the total momentum after collision. So before collision, they both have momentum. The momentum of the Volkswagen is 1,000 times 20, because it's moving to the right. And before collision, the momentum of the truck is 3,000 times minus 20, because it's moving to the left, so it's minus sign there. And since the Volkswagen has all the momentum after collision will be just the mass of the Volkswagen times its velocity. So now we can see, to solve this equation, first of all the thousands cancel off, so we can see that v is equal to 20 minus 60, which is equal to minus 40 meters per second. As a final example, let's do one two-dimensional collision. We have an 8-kilogram ball moving east. So this ball here is moving east at 10 meters per second. So we can represent the momentum of this ball by this red arrow. The length of the arrow is the product of m1 times v1, or 8 times 10. It collides with a 3-kilogram ball moving south, right here. So this arrow represents its momentum. The length of this arrow is 3 times 20, or 60 kilogram meters per second. And the question is, what is the direction of their joint velocity after colliding? So basically what we have to do is add these two vectors. Now we have to add them as vectors using the tip-to-tail method. So the red plus the blue results in this black one here. And using some trigonometry, we can figure out this information about the black one, how long it is and what direction it's pointing to. Let's take a look how to do the calculations. So the length of the red vector, we'll call that px, is equal to the m2 times v, which is 8 times 20, or 80. The length of the blue vector, we call that py, is equal to m1 times v, which is 3 times 20, is 60. And since they move together, the length of the black vector, which is their sum, is going to be m1 plus m2, the joint velocities, they're moving together, times its velocity, the unknown velocity that we're looking for here. And so m1 plus m2 is 11, 8. plus 3 is 11. So our mission here is to calculate two things: the length of this and also the angle theta over here. So let's take a look one thing at a time. First of all, let's calculate the length of the black vector. That's not too hard because the length of the black vector is just the sum of the px squared plus py squared, where px is just this and py is just that. So we write those down. We have 80 squared plus 60 squared equals 11. This is 11v squared. Now 11 squared is 121. So we can solve this equation now for the velocity. This is their joint velocity. So the second problem is, what's the angle here? What's theta? Well, we take the tangent theta. Tangent is opposite over adjacent. So opposite is 60. Adjacent is 80. So the tangent is 60 divided by 80, which is 0.75. And the inverse tangent of 0.75 is 37 degrees. So they both move off together at an angle of 37 degrees. This would be south of east, and the joint velocity is 9.1 meters per second squared.